In this video, we continue our study of Sturm-Liouville problems with an example. We are solving problem number 13 from Christian Constanda's Solution Techniques for Elementary Partial Differential Equations, second edition. We're asked to find the eigenvalues and eigenfunctions of the regular Sturm-Liouville problem. Now remember, a Sturm-Liouville problem is a second order differential equation of a certain form, subject to some boundary conditions. And typically what we're trying to find is some function that is well defined on this interval from 0 to 1 that satisfies this differential equation and the boundary conditions for a specific value of this parameter lambda. There are two unknowns in this equation, lambda and f, and you want to find lambda, which we call an eigenvalue of the Sturm-Liouville problem, and then the corresponding function f of x, which we call an eigenfunction. It turns out we're going to have infinitely many eigenvalues that correspond to infinitely many eigenfunctions. The eigenfunctions are going to be pairwise orthogonal, so we'll have just this infinite set of functions that form an orthogonal set when we're done. And our goal is to find that set. But in practice, when you're solving this, you're looking for eigenfunctions. Those are non-zero solutions to this problem that correspond to these eigenvalues, these parameter values here. But when you're solving this, you're going to go back to the same methods that you used in your ordinary differential equations class. So you're going to look at the differential equation, you're going to write that down, and then you're going to solve it using whatever method is appropriate. Now, in this case, we've got a second order differential equation. Since lambda is a real number, this is just a constant times f double prime plus a constant times f prime plus a constant times f equals 0. So that means we've got a homogeneous linear ordinary differential equation with constant coefficients. And you remember from your ODE class that if you're dealing with a homogeneous linear ODE with constant coefficients, we should let y or f of x, the function that we're looking for, equal e to the mx. And then we'll find the values of m that cause this function to satisfy the equation by differentiating as many times as necessary, substituting into the equation, and finding an equation that must be satisfied by m if this function is a solution. So that's the plan. We look at this, we recognize it as this form, or as this type of differential equation. We seek a solution in this form. Since it's a second order equation, compute f prime and f double prime, and then substitute into the equation. And simplify. So this is my f double prime plus 4 times f prime plus 3 lambda times f, which we assume to be e to the mx, equals 0. That's equivalent to this. And this exponential is never 0. So that means this polynomial in m must be 0. That's called the characteristic equation of that homogeneous linear ODE with constant coefficients. Now, if you want to, if you're comfortable with it, you can go straight from this differential equation to this characteristic equation and then solve from here. That would be totally fine. But I would recommend that if you don't know where this comes from, that you solve this, that you set this up from first principles. This will remind you that the reason why this characteristic equation must be satisfied is because we're assuming that the function has, or the solutions have this form, e to the mx. After you're comfortable with that, you can just skip all of these steps. That would be fine for somebody who truly understands where this comes from, to go from the differential equation straight to the characteristic equation. Okay, so now we're going to solve this characteristic equation for m. There are many ways you can do it. I think I'm just going to complete the square. In order to complete the square, I want to get rid of the constant term. So I will subtract the 3 lambda from both sides. And then I see I've got a coefficient of 1 in front of my m squared. That's good. If there wasn't a coefficient of 1, I would divide both sides of the equation by whatever that coefficient is. Since we have a coefficient of 1, that's not necessary. The number in front of the m here is called b, typically. I want to take half of that and square it. 2 squared is, of course, 4. So you're going to add 4 there and add 4 there. That's going to make this a perfect square. This factors to m plus 2 times m plus 2, or m plus 2 squared. And then on the right-hand side, we've got 4 minus 3 lambda. I just changed the order there. Now I want to get m by itself, so I will take the square root of both sides. Don't forget the plus or minus on the right. and we want to get m by itself. So we're going to subtract 2 from both sides. And I prefer to write it like this. I've got two values, m1 and m2. They're equal to -2 plus or minus the square root of 4 minus 3 times lambda. Now, the form of the solution really depends on the type of roots that we have here. Whenever you're dealing with a second degree polynomial, you can have distinct real roots, you can have a repeated real root, or you can have complex conjugate roots. If you're looking at this and you're like, I'm not really sure which case we have, actually we have all three cases. We will have distinct real roots for some values of lambda, and we will have a repeated root for a particular value of lambda, and we will have complex conjugate roots for different values of lambda. So let's talk through those. Let's look at case number 1. When would we have distinct real roots? Well, we would have distinct real roots if this number under the radical 4 minus 3 lambda was positive, because then I'd have -2 plus the square root of this positive number and -2 minus the square root of that positive number as my real roots. So we have distinct real roots when 4 minus 3 lambda is positive. Then we would have a repeated real root when this guy under the radical is 0, because then we just have -2 plus or minus square root of 0, which is just 0, right? And then the third possibility is that we could have complex conjugate roots. And this would be a complex conjugate pair when the expression under the radical is negative. So we want to examine each of those three cases separately, and then we'll come up with a solution to the differential equation, and then we will find the solutions that satisfy the boundary conditions that we were given for this particular regular Sturm-Liouville problem. So let's look at case 1. Let's say that 4 minus 3 lambda is greater than 0. Then we have two solutions. M1 equals -2 plus the square root of 4 minus 3 lambda. And M2 equals -2 minus the square root of 4 minus 3 lambda. Now, in that case, we have two solutions. The first solution would be e to the m1x, which is e to the -2 plus the square root of 4 minus 3 lambda times x. Multiply through or distribute that x everywhere. You're going to have this. And remember from your exponent properties, if you have x to a power times x to a different power, you would add the exponents. That works in reverse as well. Since I have a sum of exponents here, it's the same as e to the -2x times e to the x times the square root of 4 minus 3 lambda. And similarly, f2 will be e to the -2x times e to the -x times the square root of 4 minus 3 lambda. And if you're saying to yourself, how did you get that? All I did was, I said, if that was just a minus instead of a plus, I'd have a minus there and a minus there, which would make me have a minus there and a minus there. And now if you're saying to yourself, like, why would you do that? Why would you write it in this way? Well, I just want you to notice that this is just e to a constant times -x, and this is e to the same constant times +x. So these are almost identical, but they have opposite signs. And that reminds me of our hyperbolic functions. Remember from your Calculus 1 or Calculus 2 class that the hyperbolic sine of x is e to the x minus e to the -x, and the hyperbolic cosine of x is 1/2 of e to the x plus e to the negative x. I think I may have misspoke. I may have forgotten that 1/2 when I talked about the hyperbolic sign. So hyperbolic sine and hyperbolic cosine are linear combinations of exponentials that have like almost identical exponents, but with opposite signs. And that's exactly what we have here. So rather than using these two functions as my linearly independent solutions to the differential equations in this case, I think I want to use these. I want to use actually something close to these, or something, excuse me, derived from these involving the hyperbolic functions. So notice that my angle here is not x, or not angle, my argument here is not x, but it's this square root of 4 minus 3 lambda times x. So, and it's also multiplied by this e to the negative 2x. So if I were to take 1/2 of this guy, f1, and then subtract f2, I would end up with this. 1/2 of this minus this Of course, you could factor out the e to the negative 2x. That would be fine. I'm also factoring out the 1/2. And I'm putting this in brackets because I want to separate that from the e to the negative 2x. I want to separate everything else. And so if I distribute, notice that I get this back. If I distribute here, I get that second term. Now this is exactly the same form as that. The only difference is instead of an x, I've got an x times this square root of 4 minus 3 lambda. So what this is, it turns out to be e to the 2x times sine, or hyperbolic sine of the square root of 4 minus 3 lambda, that times x. And we're taking the hyperbolic sine of all of that. That's a lot. But this is just a linear combination of these two solutions to the differential equation. Since both of these are solutions to the differential equation, the linear combination of solutions is also a solution to the differential equation. And it turns out that if we do the same thing, but rather than subtracting those, we add those, we're going to get the following. We'll get e to the negative 2x times hyperbolic cosine of the square root of 4 minus 3 lambda times x. Okay, I hope it makes sense. So rather than using this is my f1 and this is my f2, I'm not going to use those anymore. I'll call those f sub 1 star and f sub 2 star. Instead, I'm going to call this my f1 and this my f2. And then I'll say that the general solution to the differential equation, or a general solution, is c1 times this function plus c2 times the second function. There should be an h there. Okay, now that is case 1 for distinct real roots. And all we've done so far is solve the differential equation in the case where that expression under the radical is positive. Okay, but we don't want to just solve the differential equation. We want to solve the boundary value problem. So we want to find the values of our constants C1 and C2 so that f of 0 is equal to 0 and f of 1 is equal to 0. So we'll do that now. If f of 0 is equal to 0, that means the following is true. F of 0 would just be this. I get C1 times e to the negative 2 times 0 times hyperbolic sine of 0 plus C2 times e to the negative 2 times 0 times hyperbolic cosine of 0. Now hyperbolic sine of 0 is 0 and hyperbolic cosine of 0 is 1. Just like sine of 0 is 0 and cosine of 0 is 1, the hyperbolic functions have that same value. that we would expect given our intuition about the trig functions. So we have f of 0 equals this. And of course, e to the 0 is just 1. So that just simplifies to C2. And we're going to set that equal to 0. And if f of 0 equals 0 and f of 0 equals C2, that means C2 must be 0. So our first boundary condition tells us that C2 must be 0. Okay. Now the second boundary condition is this, f of 1 is equal to 0. Now we already know that C2 is equal to 0. So now we're just going to substitute in right here. So f of 1 is C1 times e to the negative 2 times hyperbolic sine of the square root of 4 minus 3 lambda times x, which is 1. Now that is f of 1 in general, but we're told that f of 1 has to be 0. So we set this equal to 0, and then we solve, hopefully for lambda, like that's the idea. But look what we've got here. E to the negative 2 is just a constant. It's never 0. The only way this is 0 is if C1 equals 0 or the hyperbolic sine of the square root of 4 minus 3 lambda is equal to 0. But square root or 4 minus 3 lambda is positive. So this is the square root of a positive number, which is a positive number. And hyperbolic sine looks roughly like this. That's 1/2 e to the x, and that's a negative 1/2 times e to the negative x, and it will look kind of like that when we're done. The only time that the hyperbolic sine function is 0 is when the argument equals 0. So if this is positive, we're not going to get a 0 for this. So this has no solution. Since that has no solution, that means our only option is for C1 to be 0. So C2 is 0 and C1 equals 0. That means f is equal to 0. But we seek eigenfunctions. Those are non-zero solutions to the boundary value problem. And since that's a 0 solution, that's not an eigenfunction. So that means, that all of this means that our values of lambda cannot satisfy this equation. Or if I solve this for lambda, I get this. 4 is greater than 3 lambda, and lambda is less than 4/3. Okay. Lambda can't be less than 4/3, because if lambda were less than 4/3, then f would have to be 0, and then f can't be, and f can't be 0 because we're seeking eigenfunctions. So that means that there are no eigenvalues. Lambda that, let's say, are less than 4/3. Okay, so we've got that. All right, so that was our first case. Second case is much easier. And actually, this stuff isn't too bad. I'm just doing a lot of detail for those people who have forgotten the hyperbolic sine and hyperbolic cosine functions and how they behave. This next case is when 4 minus 3 lambda equals 0, and that corresponds to lambda equaling 4 divided by 3. Okay, in that case, m1 and m2 are equal to -2 plus or minus the square root of 0. So they're both equal to -2. So that is a repeated real root. In that case, remember from your ODE class, the first solution is e to the m1x, or in our case, e to the -2x. And the second linearly independent solution can't be e to the m2x because it wouldn't give us a linearly independent solution. It can't be exactly the same as the first solution. So we need to do something. It turns out that if f1 equals e to the -2x is a solution to a constant coefficient equation, if we use the method of reduction of order, which is also covered in the ordinary differential equations class, we can find that f2 would have to be equal to x times that first linearly independent solution. So these are two solutions to the differential equation. So that means a general solution to this differential equation is this: C1 times F1 plus C2 times F2 for some values of C1 and C2. Now we are seeking C1 and C2 so that that function does not only satisfy the differential equation, but also satisfies these boundary conditions. So now we'll use the boundary conditions to find the values of C1 and C2 that cause this function to satisfy the boundary conditions. So first we have f of 0 equals 0. That means the following. We're going to have f of 0 equals C1 times e to the 0 plus C2 times 0 times e to the 0. And of course, that's 0. So that turns out to simplify to just C1. So f of 0 is C1 in general, but if f of 0 is required to be 0 by our boundary conditions, it turns out that C1 will be equal to 0. Okay, great. And then we also know that f of 1 must be 0. And we already know that C1 is equal to 0, so we can ignore that term this time. So we have C2 times 1 times e to the negative 2 times 1. So that's C2 times e to the negative 2. And that we will set equal to 0 as well. But that exponential is just a constant. It's a 1 over e squared. It's never 0. The only way C2 times 1 over e squared is 0 is if C2 equals 0. So C1 is 0 and C2 is 0. So f is equal to 0. That would be the solution to the boundary value problem. But we're not seeking just any solution to the boundary value problem. We want eigenfunctions. We want non-zero solutions to that boundary value problem. Since we're seeking eigenfunctions, this is not going to work. So that means lambda must not equal 4/3. So we'll just say lambda equals 4/3 is not an eigenvalue of the given Sturm-Liouville problem. Okay, great. All right, so we had the distinct real roots case, we've got the repeated real root case, and now we're going to look at the complex conjugate root case. If 4 minus 3 lambda is negative, then if we multiply both sides by -1, we'll have 3 lambda minus 4. That's going to be positive in that case. And M1 and M2 are equal to this. We already did this, right? Now I can change the order there as long as I multiply by -1. So this is a -1 times a positive number. So I've got the square root of that positive number, and the square root of -1 is I. So those are my complex conjugate roots. Now recall from your ODE class that if M1 and M2 are complex conjugates alpha plus or minus beta I, the two linearly independent solutions are e to the alpha x cosine of beta x and e to the alpha x sine of beta x. Now we could write these as complex solutions, but these are two linearly independent real solutions that correspond to this complex conjugate pair. So that means our first function is e to the -2x times cosine of beta times x. And our second linearly independent solution is e to the -2x times sine of beta times x. Okay, so that is the case, or that is enough, excuse me, to get us a general solution to the differential equation. So I have C1 times F1 plus C2 times F2. Oh my goodness, there we go. Okay, now we don't just want a solution to the differential equation, we want a solution to the boundary value problem. So we want f of 0 to be 0. Now if f of 0 equals 0, that means that f of 0, which is C1 times e to the 0, which is 1, times cosine of 0, which is also 1, plus C2 times e to the 0, which is 1, times sine of 0, which is 0. It turns out to simplify to just C1. That is equal to 0. F of 0 would be C1 in general. Because f of 0 equals 0, we know that this expression has to be 0. So C1 must be 0 from the first boundary condition. And the second boundary condition is that f of 1 equals 0. Now we already know that C1 is 0, so we can just ignore this term and substitute into the second term. So you've got 0 plus C2 times e to the negative 2 times 1 times sine of the square root of 3 lambda minus 4 times 1, which is of course just itself. We want this, that's f of 1 in general, we want that to be 0 in order to satisfy that second initial condition. Now that e to the negative 2 is a constant, it's never 0. The only way that we're going to get a 0 out of this is if C2 equals 0 or the sine of the square root of 3 lambda minus 4 is equal to 0. Now, since we don't want C2 to be 0, because then we would be dealing with C1 equals 0, C2 equals 0, therefore we'd have the 0 function, and that's not an eigenvalue, or excuse me, eigenfunction. We don't want C2 to be 0, so we're going to require that this one be 0. And it turns out sine is 0 infinitely many times, so that's a great thing. That tells us we're actually going to get some eigenfunctions out of this. Now sine is 0 infinitely many times. And we know it's 0 at all of the multiples of pi. So it's 0 at pi and 2 pi and 3 pi and 4 pi and so on. And you keep going forever. But remember, we are in the case where this expression is negative, which means this expression is positive. So we are only interested in well, the multiples of pi over here, where this expression inside the sine function is positive. So we're not interested in this expression in the sine function being equal to 0. We want that expression inside to be equal to a multiple of pi. So we'll say n pi, but we need n pi to be positive. So we want this to be true for n equals 1, 2, 3, and so on. So we're talking about pi, 2 pi, 3 pi, 4 pi. I'm not interested in 0 pi or negative pi because, again, we're in this case where this is negative, which means this is positive, which means we're taking the sign of a positive number, and we want that to be equal to 0. You're saying, what would those positive numbers have to be? They would have to be this value here. Okay, so I want to get lambda by itself. So we will just square both sides. And then we will solve for lambda. So we'll add 4 to both sides. Divide both sides by 3. And now you've got an infinite family of lambdas. So instead of calling it lambda, we'll call it lambda sub n. When n is equal to 1, we get 4 plus pi squared over 3. When n is equal to 2, we're going to get 4 plus 4 times pi squared over 3. When n is equal to 3, we're going to have 4 plus 3 squared, which is 9 times pi squared over 3, and so on. So these are the eigenvalues of the given Sturm-Liouville problem. That means when lambda has lambda, which is just a real number, when that real number takes on the values here that we get when n is equal to 1, 2, 3, and so on, and we substitute those here, then this differential equation can be solved. and its solution will be the corresponding eigenfunction for each of these eigenvalues. Now to find the eigenfunctions, we're going to substitute this lambda into the form of the solution from up here. Now this just says f of x, but we could write f sub n of x because we're going to replace the lambdas with 4 plus n squared pi squared over 3. But remember that C1 is equal to 0 and C2 could be anything. So f of x is equal to C2 times e to the negative 2x times sine of the square root of something times x. So you're going to have 3 times your lambda, which is 4 plus n squared pi squared over 3. And then you're going to subtract 4 from that, all under the radical. That's 3 lambda minus 4, which is what we're supposed to have, 3 lambda minus 4 under the radical. Of course, you can see what happens. 3 over 3 reduces, and then you have 4 plus n squared pi squared minus 4, so the 4 is reduced. And then you're going to take the square root. Square root of n squared pi squared is just going to give us n pi. And so we just get n pi x. Now we don't want that constant out front. So typically we would choose C2 to equal 1. And then our eigenfunctions are e to the negative 2x times sine of n pi x. Now we'll get different functions for every value of n. This is for n equals 1, 2, 3, and so on. So yeah, instead of writing f of x over here, we're going to write f sub n of x. Okay. So our final answer is this. That's our eigenvalue, our list of eigenvalues. And then this is our list of eigenfunctions. Now I've got one formula, but remember, there's a sequence here. Oops, there's nothing under that. It's just n pi x inside that sine function. This is for n equals 1, 2, 3, and so on. This is also for n equals 1, 2, 3, and so on. Now remember what theorem 3.8 said. It said you should have an infinite sequence of eigenvalues. They should be increasing. So when I plug in n equals 1, I get lambda sub 1. When I plug in n equals 2, I get lambda sub 2. And lambda sub 1 is less than lambda sub 2, which is less than lambda sub 3, and so on. That's true. And I'll have a pi squared here, then I'll have a 4 pi squared, then I'll have a 9 pi squared. So as n increases, this increases. As n goes to infinity, lambda sub n goes to infinity. And that's all part of theorem 3.8. And theorem 3.8 also says that each of these eigenvalues corresponds to an eigenfunction. And these eigenfunctions are supposed to be pairwise orthogonal. So if you're talking about two distinct functions on this list, like with a sine of 3 at pi x, let's say, and a sine of 5 pi x, if you take the integral from 0 to 1, that's the interval of interest for us, because remember, we were starting right here. This was given in the original problem statement. And if you take this function and then you multiply by basically the same function, but with instead of an n, you have it like a different number. Instead of a 3, you've got a 2. You've got instead of a 5, you've got a 7, something like that. If you multiply like f sub 1 and f sub 3 together, or f sub 5 and f sub 7 together, and then you integrate from 0 to 1, you're going to get 0. So that means that's just another way of saying that these functions are orthogonal, or they form an orthogonal set. So that is how we solve that particular eigenvalue problem. I hope that helps. But again, you just want to look at cases. You start by solving the differential equation, recognize what type of equation it is, and then solve it. And then you're going to get some equation for your roots, and those roots are going to depend on lambda. Now, the form of the roots really affects the form of the solution. If you have distinct real roots, you get one type of solution. If you get repeated real root, you get a different type of solution. Complex conjugate roots, you get a different type of solution. Now that, whether you're in case 1, case 2, or case 3, will depend on the value of lambda. And usually there's some expression involving lambda, and you're going to see when it's positive, negative, or 0 to get your distinct real roots, your repeated real root case, and your complex conjugate root case. Okay, so you do that. After you do that, for every case, you're going to have some solution. And once you have that solution, you use the boundary conditions to figure out what the function would have to be in order to solve that differential equation and the boundary conditions at the same time. And then remember, if you ever get a 0 function, that's not the function you're looking for. You want to move on until you find functions that are non-zero functions, because eigenfunctions are by definition non-zero functions, non-zero solutions to the boundary value problem. And you just go through all 3 cases every time. So that's it for this video and that example. Let me know if you have any questions. I'll probably make another video with another example soon. Thanks, guys.